A robust understanding of memory architecture is crucial for designing instruction, supporting clients with cognitive difficulties and creating organizations that foster learning. The multi-store model and subsequent refinements articulate distinct stages and processes. Sensory memory. Sensory memory is the initial stage of memory that briefly holds incoming sensory information in a raw, unprocessed form. Visual sensory memory, often called iconic memory, and auditory sensory memory, or echoic memory, retain information for very short durations, typically milliseconds to a few seconds. Sensory memory functions as a buffer that allows further cognitive processing to select, attend to and encode information into short-term systems. Practically, sensory memory emphasizes the importance of salient and well-timed presentation of instructional stimuli. For example, simultaneous presentation of verbal instructions and visual supports should be coordinated so that learners' sensory registers capture relevant information for deeper processing. Ensuring minimal distraction and using clear, high-contrast visual materials can enhance initial encoding. Short-term memory, STM, and working memory. Short-term memory, STM, is traditionally conceived as a limited capacity store that holds information for brief periods. Miller's classic estimate suggests a capacity of approximately 7 ± 2 discrete items, Miller, 1956. Though more recent research emphasizes that capacity varies with chunking strategies and individual differences. A more functional conception is working memory, which not only holds but also manipulates information for complex tasks such as reasoning, comprehension and problem-solving. Baddeley's multi-component model of working memory posits components such as the phonological loop, verbal, auditory, the visual-spatial sketchpad, visual, spatial, the episodic buffer, integrative temporary storage, and a central executive that allocates attention and coordinates processing. Working memory is a critical bottleneck. Limitations here influence learners' ability to follow multi-step instructions, solve problems and integrate new information with prior knowledge. Implications for practice include designing instruction that reduces unnecessary cognitive load, chunking complex information into manageable units, providing scaffolding for multi-step tasks, and using external aids, for example, written checklists, to support working memory. Recognizing individual differences in working memory capacity also guides differentiated instruction and reasonable adjustments. Long-term memory, LTM, long-term memory stores information more durably and is functionally diverse. LTM can be subdivided into declarative, explicit, and non-declarative, implicit, memory systems. Declarative memory includes episodic memory, memory for personally experienced events, and semantic memory, knowledge of facts, concepts and meanings. Procedural memory, a form of implicit long-term memory, supports skills and habits that are expressed through performance rather than conscious recollection. For example, riding a bicycle. Encoding into long-term memory is influenced by depth of processing, meaningfulness, organization and rehearsal. Consolidation processes, often occurring during sleep, stabilize and integrate new memories with existing knowledge networks. Retrieval depends on effective cues and the match between encoding and retrieval contexts. In applied domains, instruction that links new material to learners' prior knowledge, employs elaborative rehearsal and uses multiple modalities supports durable learning. In therapeutic contexts, understanding episodic and semantic memory distinctions helps clinicians appreciate how traumatic experiences may be re-experienced and how cognitive restructuring can reshape semantic networks. In organizational settings, procedural memory formation underpins routine competence and the effective transfer of tacit knowledge.